Okay, let's start. So thank you very much for everybody. This talk is about making JavaScript go quickly, as fast as we can possibly make it go. Start by talking what makes JavaScript slow, how we avoid that, what sort of tricks the JavaScript runtimes use, like the V8 engine that runs in Chrome, what they use to make your JavaScript go quicker, and how we then help that runtime execute code quickly. We can give a few hints and tips. And finally, we'll look at what sort of tools we can use to help us write that fast code. A bit of background on me. I'm currently working as a JavaScript front-end developer. I'm involved in a project called OpenLayers 3, which is a open source competitor to Google Maps, effectively. The sort of stuff we do is we do nice maps. Just open that up and get the full screen. So just like Google Maps, you can pan around, zoom in, zoom out. You'll see it loads of tiles over the network connection. Slightly slow connection. Anyway, you can zoom around, zoom in, this sort of stuff. This is trying to run at 60 frames a second. So we should get 60 milliseconds per frame, and we're trying to work out what data we need to load from the server, stream it in, do all transformations, all this sort of stuff in JavaScript. So, what makes JavaScript slow? It's interpreted, we know this. A number of VMs these days starting to do just-in-time compilation, but when you do compile code, that itself takes time. So most virtual machines will only actually do the just-in-time compilation once they identify hot parts of the code. There's loose typing in JavaScript. We'll go into a bit more detail about that, but if you use a typical compiled language, be it Java or C, the compiler knows the types of all your data and can generate data structures, in-memory data structures, which match those types. In JavaScript, anything can change at any moment, and that means the compiler can't, the virtual machine can't make those assumptions ahead of time, and therefore it generates more generic and slower code. The types can change during the running of the program. You might call functions, you might sometimes pass in strings, sometimes pass objects to the same functions. We'll look at examples of that, which confuses the compiler. And another big one, fun one there is garbage collection. JavaScript's garbage collectors, it has a stop the world garbage collector. This means that if you generate garbage, that garbage collector will run, and you will get interruptions into your code. Particularly if you're trying to do something interactive, that's incredibly important to avoid the garbage generation. We'll talk about that in more detail. Another thing that makes it slow, this came up in Simon's talk, is manipulating the DOM. I'm not going to talk about that. I'm going to look more at the core of how you make your core inner loops run fast. So, what sort of tricks do the actual virtual machines use to run your code quickly? We'll go through these in a bit more detail, but you'll see the type tagging it effectively will try to determine the actual sort of classic style classes in your code. V8 uses a technique called hidden classes for this. Speculative optimization, it will try to generate code that runs fast for the particular use cases, the way it's being called in your code. Special treatment of certain types, including numerical arrays. Some machines, particularly Internet Explorer 10, for example, will compile your JavaScript, just in time compile your JavaScript in a separate thread while your code is still running, and when that separately compiled code is available, it will switch to using that version. And similarly, IE10 at least does some garbage collection in a separate thread. Let's go into a bit more detail on these. So, how are JavaScript objects represented internally? There's JavaScript objects, can be numbers, floats, strings, objects, arrays. Typically, if you just have a type tag and then a pointer to the actual value, then you have to go through a dereference to get to that actual value. This is the case in the box double example here. We have some sort of tags that can actually point to where our data is. So what we all tend to do is they take one bit of a 32-bit value to indicate what sort of type this value contains. So we know that on machines, typically pointers typically aligned on at least 4-byte boundaries, sometimes 8-byte boundaries. So for any pointer, the lower bit's always going to be 0. This gives us 3 bits and a pointer that we can then use to distinguish between different types. So as a result, we could say the lower bit is 1, we could say that's pointed to an object. And if the lower bit is 0, we can use it for something else. For example, something common is a small integer. So by actually embedding the type tag inside the word containing the data, we can avoid the extra pointing direction, and we can operate on these things directly. Notice that, just trivial things with 2 small integers, you can add 2 small integers together, and the result is still a valid small integer, assuming it doesn't overflow, but basically simple operations are now operating on single 32-bit values instead of more complicated pointer to actual data and then having to dereference like that. This, so what this means is that when you write a JavaScript function, a very simple one here, this can operate, if it's been native normal JavaScript, on both numbers and on strings. What the virtual machines tend to do is that they notice that this is only ever being called with numbers. It will generate a compiled version of this code which is specific to just numbers. This is kind of pseudocode of what it might look like. We're using the lower bit to indicate whether it's a number or an object. We check that both our arguments are actually these small objects, and if so, we use our low-level add to return the result. Well, so the virtual machine generates this sort of code when it sees small and simple functions. This code is then very fast, but if you suddenly start calling this function with different types, the compiler has to throw this code away, and you lose the advantage of it. So here's an example of what might happen here. We've got our simple add function. We call it 1,000,000 times. This is great. The compiler, the virtual machine, is going to generate that highly optimized, number-specific version of that add function. If we then call it with strings, now the compiler will throw away all that. It will see that specific version for numbers is no longer valid. It'll throw it away, and it'll go back to the slower, more generic code. So, first rule is don't mix your types up, basically. Be consistent in what you call your functions, past your functions. JavaScript arrays. This is now looking at how it's representing data. JavaScript arrays can contain pretty much anything. So the question is, how do we make them efficient? And the answer is there. Is that the compilers or the virtual machines will generate special cases for arrays when they contain all the same type. And I'll see this as an advantage for both memory layouts and code generation, and also garbage collection. So the virtual machine will try to work out if the types are being consistently used. This is a way of how will demonstrate how it fails. We create an array, we set its first element to be some small integer. The virtual machine will go, hang on, this is probably going to contain integers. It will then allocate it as just those 32-bit values with small integers. Add another element, fine, it's still going. Now if we suddenly saw a double here, now we need to allocate a bit more space for an extra element, but we've now, it'll see it's now containing numbers, but they're doubles, so we'll have to convert that small array of integers into the more generic array of doubles. Unboxed doubles means they can be stored directly in line rather than having a pointer to the actual value. If we then store something different in there, like Boolean value, now it's no longer just floats in there, and we once again have to convert that array of floats into now the more generic array of objects abstraction. So as a result, these 4 statements here have called multiple allocations and 2 conversions of the underlying type. And it's because we've been mixing our types. If you want to store those 4 different values in an array, small, just create the array straight from the start, and we'll go, hang on, okay, that's an array of objects, and we'll go straight to the most appropriate representation. So, for our objects now, in classic languages in C, you've got structs. In C++ and Java, you've got classes. Generally, these will act as, this will allow the compiler to lay out the members of that struct in memory somehow. And then to access a field in that struct, it just needs a pointer to the start of the structure and then some sort of offset to it. That's obviously super fast. In JavaScript, everything's done through property values. Your object.x, object.y, and that's more of a hash type lookup for that property name in the object. And it's much slower than that just simple offset that you get in compiled languages. So those classes that exist in other languages give you that guaranteed layout of memory. They also guarantee that certain fields will always be present. And if you've got a struct, even if it's initialized to 0, every field in that struct has value. And therefore, you don't need to test if actually things are present or not. Whereas JavaScript is a much more dynamic language. You can add new properties. You can call some object.method, and you actually have to check if method is present or not. JavaScript doesn't have any of that. It uses prototypical inheritance, which is kind of special, really, and certainly very dynamic. You can things, objects, methods, object properties can be added and removed at any time. So the question is, when these things are so dynamic, how can you share code between them? How can you make access efficient? And the trick that the V8 engine uses is it tries to detect what the actual classes in your code are. And it does that by looking at the way in which you initialize properties in the class. So I'll give an example here. So here's a simple JavaScript class. When we create a new instance of it, with new P1, the V8 engine will go, okay, I'm assigning to a property called X, and I'm assigning a property called Y. Okay, I'll create an anonymous hidden class for that. When you create a new point here, you'll go, hang on, I'm creating something with an X and a Y. It probably has the same class as the previous one. And this means that these 2 separate objects will, internally, V8 will create a virtual class, hidden class for them, and they will be able to share code. If we then go and modify one of these objects, here we're adding an extra property to P2, it no longer shares the same properties initialized in the same order, so it will now create a different hidden class for P2 and P1. So these 2 will no longer be sharing code. So the golden rule there is use classical style classes, always initialize properties in the same order, and the runtime will create these hidden classes for you. Here's how not to do it. This is how to write JavaScript code which has a pretty API but runs slowly. We're quite used to these fluent interfaces where you can chain methods together. Methods can take different number of arguments, different types. Here's an example for creating a simple circle. But what we might also want is have the center method, when called with no arguments, return the center of the circle. We might want to be able to set it using an array or maybe an object literal in there. So here, this center function, it gives us this lovely API where we can just chain stuff together, but this center function has very different behaviors depending on its arguments. How will you actually implement that? This is what the code tends to look like. If the arguments return the center, otherwise we check through what we actually got and operate appropriately. what happens here is this sort of code is really hard for the VM to optimize because it gets called multiple different times with different types of objects, sometimes strings, sometimes arrays, sometimes objects. And so cannot generate specialized code that just, if we just had one single word calling it, the VM could generate a specific code for it, but with this sort of loose typing approach, you'll never go. So, what should you do to write fast code? Use types consistently. This is the most important thing. Basically, if you want to provide flexibility for these sort of things, make these different things separate functions. Call this one get center. Call this one set center with array. Call this one set center with object. And by having different functions, the VM will be able to specialize each one for you. Don't play with types at runtime. Once your objects are created, try to create all the properties in the constructor, and then don't touch their classes. Don't add extra methods to your objects. That way, that way the compiler, the virtual machine, all the assumptions, it will be able to make strong assumptions about your code, and you won't break them. Initialize all properties in the constructor, or always initialize properties in the same order. That's for the hidden class stuff. Don't mix types and numeric arrays. That's the layout stuff here, so that the virtual machine can generate, for example, special stuff, just the doubles, just the integers. The V8 engine has got a nice little feature. It will actually tell you when it optimizes code, when it just-in-time compiles one of your functions, and also when it deoptimizes. And it deoptimizes when the assumptions it made turn out to be invalid. Say, we go back to the example where you called add a million times with numbers, that'll optimize it. You call add with strings, then it deoptimizes. You can actually, with a couple of command line flags, you can get a tell you, and then you'll see where your code is, you're breaking these assumptions. Garbage collection, the next topic. So garbage collection is critical in JavaScript, especially if you want to run interactive applications. It's a total to stop the world, so there's nothing you can do to get around it. The language itself generates a lot in the way that you use JavaScript. We're very used to creating object literals, arrays, all the way through the code. But if you want high performance, you just basically have to avoid generating garbage in the first place. So here's a fairly trivial example. This is a simple function here. Our point class again. We've got a distance function which takes this another point. Here, now let's call this function. So we'll distance from origin. To call this function, we need to create a new point object. This point object here only needs to exist for the execution of this function. After this call returns, that object is now garbage. We don't need it anymore. As a result, this is calculating different distances between points is a pretty basic thing. But now every single call to this function will probably generate a piece of garbage. Over time, that accumulates. It's not good. So how do we refactor our function? If instead we destructure our data, instead of having distance to point, we pass in two numeric arguments. Now we have the same functionality, but we don't generate any garbage when this function is called. So as a result, although the API is arguably less elegant, in an inner loop, this sort of code is going to generate less garbage, which is good. Here's quite an interesting set of points. Here's an example of an array with a million or so numbers in it. So integers, that's fine. Now I'm going to set one of the elements in here to be an object. This is going to have two very bad effects. The first effect we saw earlier, previously this would have been optimized to be an array of integers. At this point, once we start to store something different in there, in this case, it's going to have to reallocate that entire array to convert it from an array of integers into an array of arbitrary objects. which is bad thing number one. Bad thing number two is what's related to garbage collection. Most garbage collectors work by working through your data structures and working out what's reachable. An array of numbers only contains numbers, it doesn't contain references to any other objects. Once it gets converted into an array of arbitrary objects, to actually traverse that data structure, you have to inspect every element to say, is this a point to is it an object, or it might have to be garbage collected, or so suddenly we've gone from a single object might be that cannot contain references to any other objects because we know it's just integers, to a very large array which might contain references to other objects and therefore needs to be traversed by the garbage collector. So don't do that. So still on the themes of how to reduce the garbage collection, the impact on garbage. In this particular case, we've got a few points to represent. Here we have, I think, a total of 4 objects. We've got 3 point objects plus an array to hold them. If we switch to this sort of structure for our data, we've still got 4 objects, so it's now with 3 arrays of small integers and 1 array containing arbitrary objects or array of integers. So that's already much better. We know that arrays of integers can't contain references to objects, so the garbage collector will traverse that very quickly. We can further destructure our data, and if we remember we have a sort of spacing here, by this point, if we can write our data this way, we've got a single array, cannot contain objects. This is going to be handled super efficiently. Of course, handling data in this form is probably more awkward than handling it in this form from a programming point of view. I mean, that's the trade-off that you're making. But the net result is you'll get much better garbage collection performance rates. So, this is what you should know. Try to avoid creating objects. Reuse arrays and objects. Rather than throwing away an object once it's used, clear all its members and reuse that same object instance. And similarly, if you need a new array, instead of creating a new array containing results, set your length of an existing array to 0 and start reusing that. So consider destructuring your data. That's what we're looking at there, the example of points. It generally makes more complex code, but it can give you a big performance boost, particularly on the garbage collection front. And Chrome, I'm sure you're all used to the timeline in Chrome, it's got some fantastic tools to spot problems. The classic one, which I was trying to do actually. Who's used the who here has used the developer tools in Chrome? Yeah, excellent. Have you looked at the profiles at the timelines? Yeah. And you've seen the JavaScript this application's got reasonable performance in it. So the key thing is the memory. This is as our code runs, we're generating garbage, and then every now and then this garbage collection cycle shuts up, and then we start accumulating. This application has actually got reasonably quite a lot of work to reduce the garbage generation. And the result, the gradient of that line is quite flat. If your application is promised, if you see really steep, lots of allocation memory, regular garbage collection cycles, then that's a good clue that you need to look into your garbage collection problem. But the Chrome tools are fantastic for that, so do use them. So slightly different tack now. There we talked about how you write your JavaScript code to go fast. What tools can you use? There's a number of ahead of time compilers available at the moment. There's a list of a few of them there. And these generally take JavaScript or some JavaScript-ish language as input, and they generate a better JavaScript as output. What do they have in common? Particularly the Google Closure compiler Dart and TypeScript, is they look a lot like Java or C++. They use classical style inheritance. And the reason they do that, rather than the sort of funky JavaScript style inheritance, is because that classical class-based inheritance is what's easy to optimize. It's what the virtual machines optimize the best. So as they care about performance, they stick with our classical Java style stuff. They typically involve some sort of type checking in there. There might be optional annotations in the case of Closure compiler. We'll do a quick example of that. But the fact they do use type checking encourages you to write functions that always take the same type and therefore be well optimized by the virtual machine. They some will do some quite advanced optimizations, including inlining functions in JavaScript for you. And specialization means that they will generate specific. They will how to put this. The Closure compiler, for example, does whole program optimization. And if you have a function that says 2 arguments, and you only ever call that function where the second argument is 1 throughout your entire program, then the compiler will say, hang on, that second argument is effectively constant in this function, and it will generate a special version of your function which only takes 1 argument, assuming the second argument is 1. It's really, there's some pretty sophisticated stuff there. To give you, just put some numbers on what the Closure compiler does. In this Open Layers 3 project I'm working on, our code base is about 1 megabyte of JavaScript plus the Closure library. The Closure compiler compresses it down to about 25% of that size for gzip to get about 2050k, and by the time you gzip it's down to 100k. It's massively reducing the size of JavaScript, and it does a whole load of other stuff. The compilers also do temporary object elimination. We looked at the example of the point, where we had to create a point object called distance to, and we destructured it into having 2 arguments, separate x and y arguments. The compilers will do a lot of this sort of stuff for you, if you're and automatic data destructuring in some cases, it will flatten out objects for you. If you have lots of nested objects and you can work out that these things don't conflict, it will turn into flatter objects. This is an example from the Closure compiler. I'm not going to go into the details of what we're doing. It's a fantastic piece of software. It's kind of halfway between JavaScript and Java, basically. We write JS.style comments, where you can give types. And the compiler, and then we write fairly classical JavaScript. The compiler it will do multiple things, but it will the type checking means that it will catch us. It will catch if we ever try to call us with the wrong type, then we write strings. It will generate a very small, minimal version of this function as well. The actual compiled version of that will probably be about 10 bytes. So I will show you examples if you're interested afterwards. I don't go into okay, so some of the tools we can use. Other ways to make your JavaScript run fast. And actually, something we do is don't use JavaScript. And there's no large amount of native code that you can take advantage of. And look at some of these examples. For example, built-in methods in the same. CSS. If you're doing animations, rather than moving stuff yourself, use CSS animations from the browser. They're native code, they're going to run quick. You've got APIs like Canvas, WebGL and WebCL, which all give you basically high-level access to. Sorry, what's that? You don't need to write your own graphics. You can use effectively native code libraries directly from JavaScript. The example with Canvas is you've probably seen the heat maps sometimes on Google Earth or on Google Maps. With these things sort of coloured intensity according to some value. Okay, so you've got internet range. But these sort of heat maps are actually generated using the Canvas API. And if you can use this correctly, you can get it to do all the additions for your native code rather than you having to do it in JavaScript. I'll give a quick example of So here's an example of exploiting native code. Here we're trying to find the smallest value in an array. It's generally pretty straightforward code. Just look over it, find the smallest. Can we do better? Well, we can actually. The JavaScript itself has got a math.min function, which can provide as many arguments as you want to. And here, this application, this loop now is now going to run native code. And that's going to be faster than writing in JavaScript ourselves. As a final example, I want to talk about something called asm.js. Who's most of you heard of it? Yeah. So asm.js came out of the InScript and C to JavaScript compiler, and basically it looks like, how to put it? It looks like assembly language, except it's JavaScript, and it has a number of distinctions. So basically, InScript generates JavaScript from C. How does it do this? So rather than C has manual allocation with malloc free, doesn't have garbage collection, so they just allocate a huge array and say that's my block of memory, and they do their own effectively low-level allocation within that block of memory. That means that the JavaScript garbage collector never runs on it, or doesn't run very often, but it certainly. So that eventually solves a lot of the garbage collection problems. Use type coercions to get types. I'll demonstrate that in a sec. And finally, what's very interesting about asm.js is that it's a strict subset of JavaScript. This means every asm.js piece of code is also valid JavaScript, which gives you immediate backward compatibility. This is what asm.js looks like. Here, I've created a module with two functions in it. So inc will increment integers only. This bitwise OR with 0, it forces this x to behave, it will force x to be an integer. And similarly, the logical OR is 0 on the return value ensures that it overflows at 32 bits, which is the way that these integers should behave. By prefixing the plus, we force things to be doubles. Actually, whatever type it was before, it's now a double after this. And similarly on the return value. So the net result is that these are both valid, this is all valid JavaScript, but the asm.js pass will go, hang on, this guy's all about integers and will generate good native code, assuming x is an integer, in this case all about doubles. And in practice, asm.js is actually getting within a factor of 2 of native code now, which is pretty good, really. Typically, you wouldn't want to write your entire code like this. You want computers to generate this sort of code for you. You don't want to write asm.js by hand, but you do want to call it from your application. So you typically wrap it up in some sort of module and just call it up. And just to give you an example of asm.js, I'm sure you've seen this. This here. So this is the Epic Citadel demo, which is a C program. It's actually running in the browser, all compiled to asm.js. I've got a fairly old Mac, so it's not super fast. You get this is pretty impressive performance for me. It's using WebGL for 3D graphics. There's lots of nice reflections in there, and it shows that really in the browser you can do pretty cool. You can really do some pretty cool stuff. I encourage you to play with it on your machines. So, a summary on how to write fast JavaScript. Be consistent with your types is the first one. Use classical programming patterns. I know JavaScript's funky, but classical style inheritance, it'll make your code quicker. Use native code where possible, and that could be either calling right JavaScript functions or using external libraries, WebGL, or the libraries like WebGL, Canvas, and so on. Reduce garbage collection through techniques we talk about, and of course, finally, you need to measure it. You use the tools available on Chrome DevTools. If you're more interesting, look a bit more details, some fantastic resources out there. this talk, Breaking JavaScript Speed Limit V8, is with the Google V8 guys who did it. The talk itself you can find on YouTube. It's quite long and and it's not fantastically presented, but the slides are fantastic. So I strongly recommend when you go to find out more detail how this stuff works. It's a fantastic resource. It's very hard to find stuff about what goes on in IE10, the Windows machine. I've just found one resource that talks a little bit about what they're doing. IE10 is not too bad in JavaScript. It's got some way behind. It's a lot better than the previous slides. So that gives you a little bit about what they're doing. And the final one is a blog article which goes more into ways of avoiding garbage. And that's it for me. Thank you very much. Any questions?
You showed the example where the pretty API was stands against the performance.
Yeah.
What is actually the slow part? That the way it's called during the program, or the way it is written?
No,
the prototype center, is that the issue, or is the way it's called above the issue?
It's a very good question. It's the way it's called that is the problem. If it was just always called one way, or a single way, let's say simply that it's always called without arguments, then the virtual machine will generate basically just this code for it. But it's once we start calling it multiple different ways, that specialized version function is no longer valid, and it has to go through the slower sort of multiple checks.
And what would you say about those type checks? I used to do it when I write a framework,
Yeah.
because I don't know how they are going to call it. Can I check it as a precompiler or something?
Yeah.
So is this a performance issue in general?
It's if there's any inner loops, it can be, yeah. I mean, we like to write. It's convenient for users to have functions be called in many different ways. So we do the work of type checking. Did you give us a string? Did you give us a number? Did you give us an object? That makes nice APIs, but it doesn't compile well.
Okay.
So my recommendation there, if you care about speed, is either insist that people always call it the same way, or they always call it with numbers, or they always call it with strings, or do separate functions for the different types.
Okay.
In the case, if you're using something like Dart or TypeScript or a closure compiler, it will do that type checking for you.
Okay.
So
during runtime too? So
no, only during compile time. But if you compile your application, your library together, then you'll get a whole thing properly typed. Cool. Thank you very much.